Hello, hello, hello. Can everyone hear me? Yes. All right. It is time to begin the next session. If you could take your seats, that would be much appreciated. This session is Astrophysics Enabled by the Moon, and it will have 3 talks followed by a 15-minute discussion or so. Our first speaker will be Jack Burns from the University of Colorado, and though he was my thesis advisor, he will receive no special treatment with regards to the time. So.
Thanks, Jordan. It's always good to be loved. So, my colleague Terry Fong did a great job of providing an introduction to the Lunar Orbiting Platform Gateway, which, according to Ben, is now just simply the Lunar Gateway, right, Ben?
You're behind the time.
Yeah, behind the time. So, yeah, this abstract was put in months ago. So, yeah, it changes daily. I don't know what it'll be tomorrow, but what I'd like to do today is follow up on what Terry was describing and focus specifically on the use of the gateway for low latency surface telerobotics. Talk a little bit about the science, although I'm going to talk more about really the facilitation of telerobotics from the gateway. So let's see, I think I can do the next slide this way, maybe this way. Here we go. So here is NASA's new graphic for the Lunar Exploration Campaign. I love this graphic because look at the moon. It's so nice and big. Compare this to a similar graphic just a year ago where the moon was just this tiny little thing. It was hardly there. And so the moon obviously is the next destination for NASA and the international community who's been pushing this for a decade or more, and facilitated by NASA's SLS and Orion, but also by a number of commercial companies who will be participating as part of public-private partnerships. We've got the gateway there, we've got robotic surface rovers, we've got human landers that will be so, and it's an exciting time that we're moving into, and we think that surface telerobotics will play an important role early on. As Terry mentioned, surface telerobotics now is built in as a requirement for the gateway. And so now it's about deciding on what we're going to do and how we're going to facilitate this. So a number of us have been pushing surface telerobotics for the better part of a decade. Terry and his group put together this roadmap a few years ago that started off with ground analogs that he and his team have been working on for some time. That led to these ISS laboratory experiments that Terry mentioned and I'll talk a little bit more about. Now, finally, we're ready to go to lunar orbit with the gateway, and much of what we'll learn in this process is going to feed forward to Mars as well. Likely the first orbiting human missions will very much utilize teleoperation of rovers on the Martian surface. So this experiment from several years ago using the ISS started off with this K-10 rover Terry showed briefly. This is on the Lunar Roverscape, as it's called, right here at NASA Ames. And you can see several cameras. I guess there's a weird pointer here. Several cameras up over here. There's a LiDAR, which is used for hazard mapping. And you can see the terrain, which is attempting to approximate a little bit of what a lunar body would look like. Ashkana, yeah, if you could start that out of video. This upper one is the second session that we ran with Italian astronaut Luca Parmitano. And Terry showed a little bit of this, and you can see that the interface, which was designed by the Intelligent Robotics Group here at Ames, is running on a simple laptop, a Lenovo laptop, and you can see the terrain mapping, the hazard map, if you will, and Luca Parmitano navigating through the hazards. And then down below over here, in the lower right section are real-time images which were being sent to the space station. Down below is the essence of the experiment, and that is we were trying to mimic how we might go about deploying a backbone for a low-frequency radio telescope using polyamide film that you see over here. So my students and I built this deployer on the back of the K-10. And eventually this would have a series of metallic dipoles that would be embedded onto the polyimide film and then electronically activated and phased to take data. So this was an experiment to demonstrate more about the deployment characteristics. The result of that second session, we had a total of 3, is shown here. And the 3 arms of the array are shown here, very much like a VLA, a very large array, such as what's in New Mexico in terms of the deployment. So here's the third session. The third session was dedicated to both deployment and also inspection of the polyimide film. And so all 3 of these were very successful. Here's the test configuration. What was neat about this is we turned the usual operation on its head. That is, usually you have ground controllers operating space assets. Here you had astronauts in space operating ground assets for the first time. And that was neat. A schematic of how this worked is, once again, you have the laptop over here, downlinked instructions with a plan to the rover. The rover in turn sent data back to the ISS, both images as well as other telemetry data. We didn't have, of course, direct line of sight communication between the ISS and the ground, as we will have with the gateway and the lunar surface. But even so, going through TDRS, there was only about a half-second delay. So that's very comparable to what we expect to have with the gateway and the lunar surface. So it was reasonably realistic in a number of ways. Here's just another look at the robot interface that Terry and his team designed. And once again, you can see here the terrain hazards and the mapping that was done, and then the visible wavelength imagery that's over here. It was very much like a video game, and the astronauts came up to speed on this extremely quickly. We only had 2.5 hours total for each session, each of the 3 sessions, and that had to include training as well as execution. So it demonstrated that in many ways, the success of being able to do this. We developed a number of metrics to measure and assess the approach, some of which are shown here, looking at things like robot utilization, task success, performance, and then a series of crew questionnaires at the end that attempted to measure workload and situation awareness. And those were all summed up, put together in a series of papers presented mainly at conferences to date. So here's a visual summary of the 3 sessions. As I mentioned before, survey to begin with. Second session was deployment. Third session was deployment and inspection. And sort of a high-level summary of what we had here. We found the crew maintained good situation awareness throughout. The rover utilization was good. And very importantly, the crew stated back to us in the surveys that the workload was low, so that we could maintain in the future operation of multiple rovers at the same time, which is something we'd like to do with both from the gateway as well as astronauts on the surface tasking out a series of rovers. So the next stage, as I said, is Lunar Science from the Farside, utilizing the gateway. Terry mentioned the gateway would only be occupied 30 to 60 days a year initially, but it will be operated as a planetary science asset during the rest of the time. And with the orbit that's planned, it'll serve as a communication relay from the Farside to the Earth, facilitating surface telerobotics, kind of radio astronomy that we were talking about before, deploying antennas, and also sample return, which my colleague David Kring has worked on a good deal in collaboration with us on it. So David's talked about this individually. Last couple of things I want to present is just some additional work that my students and I have been doing recently towards being able to construct an array on the moon. Here's some laboratory work that 2 of 3 of my undergraduate students, Alex Sandoval and Arun Kumar, who are here and have a very nice poster, including both the rover that we're using for this experiment and a new robotic arm that we put into place. The idea behind this project is to work through what are the challenges associated with actually taking components of radio telescopes off of a lander, assembling together, connecting them to computer and power control, and then actually operating. And that's demonstrated here to some extent. This is a monopole antenna and a holder which was 3D printed, and then down below shows the power connection with a micro USB. If we could go ahead and play this little video which shows a summary of this operation that the students put together. So we did 3D printing of these components that you see down over here. One of the reasons I really wanted to push this was because it's possible that rather than bringing all these components to the moon, we can bring a 3D printer and utilize some of the stock material on the moon to print them. This is the rover, this is the arm, which we call Armstrong. Seemed to be pretty appropriate. The students came up with this name, so. Nice job. Here's Armstrong picking up the micro USB and the power connector, and it's going to install it with using the magnetic micro USB onto the location where the antenna is. Power computer connection, and then it takes data. This is a plot of time versus frequency over here, what we call a waterfall plot. And then we also took a Fourier transform to look for periodicities. So what we've done here, very important discovery, we've rediscovered the FM band. So, but again, it just illustrates that operating at around 90 to 100 megahertz is possible to do. The last thing I want to show is a second project that, if we have the next, oops, I can do that, next slide. Is a virtual reality simulation test bed that Michael Walker has been working on. He's a graduate student at the University of Colorado, and this is a collaboration with David Kring and Jen Hellman as well. The idea behind this is to use a virtual game engine, Unity, to simulate having rovers on the surface to do rapid prototyping. One of the work that Michael has done recently, if we could turn on the middle video, is an example of what you might be able to do with a combination of virtual and augmented reality. Much more powerful than just the kind of flat screen Telerobotics that I showed you with the astronauts. Here you have a headset. The astronaut, by moving the head, can navigate the rover. The augmented reality points to the direction that the rover is moving in. The little circle over here is a fuel gauge. So it shows you the power of taking that next leap in technology. One of the other things we're doing is, this is a synthetic lunar terrain. We're moving to a more realistic terrain that comes from working with collaborators at the Resource Prospector group. So let me just, I know I'm running a little late on time here, so let me try to just go to the last slide with a summary. So the gateway is opening up, particularly the Lunar Farside, for important science, and we're beginning to take some steps along the way to prepare for the deployment of radio telescopes. I'm done.
Quick question or two for Jack.
Crickets. Ben, come on, question now.
What is the scale of the rover that you need to lay out the Mylar film?
Not very big. Something that's sort of, size of this desk that we have over here, this podium, in terms of width. So a small rover, not a gigantic one. So something fairly modest. To do it this way, we're also looking at, as you saw with the student experiment, individual dipoles laying down. Again, that would be a modest-sized rover.
In any of your simulations, have you simulated the stark lighting conditions that you would have on the moon?
Sorry, in what respect, the dark lighting conditions?
No, the stark lighting conditions. You don't have an atmosphere on the moon, you have very...
The stark.
Stark.
Sorry. I got you. Yes, yeah, that's an excellent question because we have the capability of building in, we already have some significant physics modules in here. So one of the things we want to study is, in fact, the effect of lighting conditions at different elevations of the sun and filters that could mitigate this. As well as soil properties. So that's the plan. We're just in the early stages, the beginning stages of this, but that's very much on our minds.